Hey everyone, and welcome to another deep dive. You guys sent in some seriously interesting stuff about space and time, and let me tell you, this one's a real doozy. We're talking time travel. Well, kinda.
Yeah.
More like we're gonna break down the physics that suggest it might, just might be possible, and who better to be our guide on this wild ride than the one and only Albert Einstein. So picture this. You're strapped into a spaceship, engines are roaring, and you're flying through the cosmos at, a ridiculous speed. Stars are whizzing past you, but here's the thing.
No matter how fast you're going, even pushing close to the speed of light from those stars, it's still traveling at, well, the speed of light relative to you. This is like the cornerstone of Einstein's theory of special relativity, the idea that the speed of light, it's constant.
Whoa, okay, so even if you're in a super fast spaceship, light's still playing by its own rules.
Whoa. Exactly. It's like a universal speed limit, no matter how fast anything else is moving.
And my brain's already starting to hurt, but this is seriously cool stuff. So how does that even work? If the speed of light never changes, but speed is all about distance and time, something's got to give, right?
You got it. And what gives is our understanding of time itself.
Time? Wait, so you're saying time isn't like a constant thing?
You're catching on quickly. Time isn't this rigid, unchanging thing we experience day to day.
Whoa. Okay, so how do we wrap our heads around that? If time isn't constant, what is it?
Think of it less like a river that flows at the same speed everywhere and more like a dance. The tempo can speed up or slow down depending on how you move.
Okay, I kind of get it, but this is some next level thinking right here. So if the speed of light is constant and speed is distance over time, something's got to budge when you're moving super fast, right? What's the trade-off?
You're right on the money. The trade-off, my friend, is time itself. It's a mind-bending phenomenon we call time dilation.
Time dilation. Okay, yeah, that sounds pretty intense.
Mm.
I am definitely intrigued, though. Tell me more. Time dilation. It sounds like something straight out of science fiction, you know? So is this like a real thing or just some crazy theory physicists cooked up?
Well, that's the wild part. It's not just some theory. We've got actual proof that time dilation is happening.
Really?
Yeah, and some of the most convincing evidence comes from these things called muons.
Muons. Those subatomic particles, right? They're like heavier electrons, as I recall.
Spot on. Muons are created way up high in the atmosphere when cosmic rays hit the Earth, and they've got a really short lifespan, like super short.
Okay, but we do have muons down here on Earth, don't we? How'd they get here if they decay so quickly?
That's the million-dollar question, and the answer lies in time dilation. See, because they're zipping around at a good chunk of the speed of light, time actually slows down for them relative to us down here.
So their internal clocks are ticking slower, giving them more time to reach us?
Exactly. They essentially get a longer lifespan from our perspective, which allows them to make the trip down to Earth before they disappear.
Whoa, tiny particles bending time. That's nuts.
It's like they're taking a shortcut through the fabric of reality. And get this, it's not just particles. Even astronauts experience time dilation, though on a much smaller scale.
Oh, yeah. Like, how much are we talking?
It's tiny, but measurable. Remember Sergei Krikalev? He spent over 800 days on the International Space Station.
Oh, yeah. Wasn't he, like, orbiting Earth crazy fast?
Exactly. And because of that speed and the length of his mission when he came back to Earth, he was actually a fraction of a second younger than he would have been if he stayed put.
Wait, so you're saying because he was moving so fast up there, time literally slowed down for him?
Yep. It's a tiny difference, sure, but it proves that time dilation isn't science fiction. It's a real phenomenon that we can observe and measure.
My mind is officially blown. Okay, so let's say, hypothetically speaking, we could travel even closer to the speed of light. That time difference would be a lot more noticeable, right?
You're on the right track. Imagine hopping in a spaceship flying at, say, 99% the speed of light for a year. When you get back to Earth, decades could have passed.
It's like that movie Interstellar, where the astronaut dad ages way slower than his daughter back on Earth because he's hanging out near a black hole.
Exactly, except in this case, it's not science fiction, it's rooted in real physics.
Time dilation. A one-way ticket to the future, maybe? Wild. So, what other mind-blowing implications did Einstein uncover about the universe? Okay, so you mentioned there was another crazy consequence of special relativity. Lay it on me. What is it?
Get ready for this. We're talking about space itself shrinking. It's called length contraction.
Length contraction. Now things are shrinking. I thought we were messing with time here.
It's all connected, remember? So picture that spaceship again, zipping through space at near light speed, heading for some distant star. Well, not only is time slowing down for you, but the distance you're traveling, it actually appears to shrink.
Wait, so the closer you get to the speed of light, the shorter your trip gets.
Exactly. The distance between you and that star, it contracts in the direction you're moving.
Okay, hold on. This is messing with my head. It's like saying the faster you drive, the shorter the road gets.
You got it. It's kind of like that, but on a cosmic scale.
Hmm.
At these incredible speeds, the distances between objects moving relative to you, they literally shrink.
So if I were a beam of light zipping across the universe, would everything just be like squished flat?
You're pushing it to the extreme there, but you're getting the idea. It's all relative to your speed. The faster you move, the more space compresses along your direction of travel.
So it's not like the star is physically shrinking, right? It's more like our perception of the distance changes because we're moving so ridiculously fast.
You nailed it. And that's the mind-blowing thing about special relativity. It tells us that space and time, they're not these fixed, unchanging things we thought they were. They're fluid, flexible even, and they're intertwined in ways we're only beginning to understand.
This is seriously blowing my mind. Time can slow down, space can shrink. There's got to be some kind of catch, right? This can't be how the universe
Ugh.
works.
Well, you're not wrong to question it. It's a lot to wrap your head around, and it leads to some pretty mind-boggling paradoxes. One in particular really highlights the weirdness of it all. We call it the twin paradox.
The twin paradox. Okay, you've got my attention. Hit me with it.
So imagine you have two identical twins. Let's call them Alice and Bob. Alice, the adventurous one, hops in a spaceship and blasts off into space at near light speed. Bob, on the other hand, stays here on good old Earth. Now, Alice, she zips around the cosmos for, say, a year, exploring new galaxies, living the spacefaring dream. Then she turns that spaceship around and heads back home.
Okay, I'm following so far. So Alice has been gone for a year, right? What about Bob? How much time has passed for him?
That's the kicker. Because Alice was traveling at near light speed, time slowed down for her, remember. So while only a year passed for Alice, decades could have gone by for Bob back on Earth.
Wait, are you serious? You're telling me that Alex could come back to Earth and her twin brother would be like an old man?
That's the paradox. And it gets even weirder. From Alice's perspective, she was just gone for a year, living her best life. From Bob's perspective, he's been patiently waiting for his sister to return for decades, watching the world change around him.
Whoa, this is seriously messing with my head. But it's based on real science, right?
It is. The twin paradox highlights the fact that time is relative.
Mm-hmm.
It's not this absolute unchanging thing we experience in our everyday lives. It can be stretched, compressed, even warped. It all depends on how fast you're moving.
So what you're saying is if I want to stay young forever, I just need to find a way to travel at the speed of light.
Well, it's not quite that simple.
Hmm,
But who knows what the future holds? Maybe one day we'll crack the code of time travel.
that would be something else. Well, listeners, I hope you've enjoyed this wild ride through the mind-bending world of special relativity. We've covered a lot of ground today, from time dilation to length contraction and that crazy twin paradox. It's enough to make your brain melt a little, but it's also pretty darn exciting, right? Just goes to show that the universe is full of surprises, and the more we learn, the stranger it gets. That's all the time we have for today's deep dive. Until next time, keep looking up at the stars and never stop questioning the nature of reality.